Hey, recorded is rolling. So it's Tuesday, January 17th. I come back from 2-day weekend with Martin Luther King Day. Gonna go over AP Classroom today. First got guys started, I remember right before the weekend, so we already did the first few. Tomorrow I'll have an experimental design FRQ lined up for you guys on, Unit 6, Software for Emotion. So if you're ready to do that, that's one of the longer ones, right? In May, you guys are gonna get 5 FRQs. 2 of them are like long 12 pointers, and we're gonna practice one of those tomorrow. It's gonna be in-class quiz on Thursday. Yeah, let's go ahead and do open notes for this. Now, you guys know open notes, that doesn't mean don't study. That means study really hard because you guys don't go through, you got some challenging questions. So you have to know like exactly like how to solve stuff and where to go to figure out, okay, right. Have everything in hand, like you have to know like how to solve stuff, right? All right, and then plan on Fridays to go over midterm solutions. So, right, well, that's kind of got. So see how close we can stick to that. Right. Right before we jump into AP Classroom, I want to go back and look at the one problem that stuck to me back last week. You guys remember outdoor market, bunch of bananas? You guys remember that? It's like so put bananas in the tray and it's on the spring and wow, 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 bounces up and down. Okay. So I showed you guys one way to solve that. That was a little bit lengthy. It went through the oscillatory motion, like finding cosine graphs and the whole deal. Okay. Then went home and realized, oh, actually, there is a more straightforward way to solve this. That here, I'll show you guys the way we did it. So we got the bananas uh in the tray. It's on the spring. We're gonna pull this down, let go. Wow, 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 wow. And they told us 3 things. Okay. They said the spring constant K is 16 Newton per meter. They told you the amplitude of motion, which is like how far up and how far down from equilibrium position, was 20 centimeters. We'll go 0.20 meters, I could call it, right? Okay. And that the max speed, so going through the center, going through the equilibrium point, that would be the place for max speed, right? Because it'd be 0 speed at the top and 0 speed at the bottom, but max speed at the middle. Okay, so V max was 40 centimeters per second. Maybe I'll call it 0.40 meters per second, just to stick in base SI units, right? Okay, so what it was is you could actually solve with conservation of energy, sum of energy initial equals sum of energy final, and you get the same answer. The question was what's the weight of the bananas, but really solve for the mass first, and then just multiply by gravity field to get the weight, right? Okay. So really, we're going to solve for the mass of the bananas. Okay. You can solve this whole thing just by saying 1/2 Ka squared, because amplitude is like the maximum stretch amount, and if it is maximum stretch amount, then all the energy you could consider as being stored in the spring is equal to 1/2 mv max squared, because if it's going through the equilibrium point, then you consider the spring not stretched. Now, I threw this out a few. I remember why I threw this problem out a few years ago. And it's like, I don't want to mess with this. It's because I could totally buy this for horizontal. Like if the spring was oriented horizontally, it's like, okay, this totally makes sense. But when it's vertical, it's like, oh, well, what about like gravity? It's going against gravity. You got this extra spring stretch, blah, 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 blah. And I remember going through like lots of paper many nights, many years ago, and it's like, I don't know, I just wanted to deal with it. But anyway, this just gives the same answers we got going through the longer method from last week. Because like we have check, so you can just solve for check, right? Get the same thing, like 4 kilograms, therefore they weigh 40 newtons. So I think the takeaway from this is that whether the spring is oriented horizontally or vertically, see if it is oriented vertically like this, you can treat it with the exact same physics as if it's oriented horizontally, where the equilibrium position here, where the spring actually is stretched a little bit, you could treat as the true equilibrium position in a horizontal orientation. Okay, so there you go. There's another way to solve it that I think intuitively makes less sense, but it actually gets you the same answer, and it's actually easier to it's faster to solve that way. All right, so you guys ready for AP Classroom? And so let's switch this over and do some AP Classroom.